Welcome to YU. In the last lecture, we saw how an augmented matrix can be simplified through the process of Gauss-Jordan elimination. This is accomplished by performing a sequence of elementary row operations which simplify the matrix one entry at a time until the matrix is in reduced row echelon form. If the system of equations has a single unique solution, the end result will be a matrix whose coordinate entries are all ones along the main diagonal of the matrix and zeros everywhere else. Since a system of linear equations in three variables is graphically represented by a collection of planes, following how these planes change their orientation with each row operation can help give us an intuitive understanding of how the transformation to reduced row echelon form works. So what effect do each of the three elementary row operations, swap, scale, and pivot, have on the planes? The swap operation has no effect, since it only changes the order in which the matrix rows are listed. Likewise, the scale operation, which multiplies any row by a non-zero constant, does not affect the planes, since any multiple of a matrix row has the same graph as the original row. Only the pivot operation changes the planes, since adding a multiple of one row to another row changes the solutions and graph of the equation which that row represents. So how exactly does the orientation of the planes change when a pivot operation is performed? In the lecture entitled A Geometrical View of the Elimination Method, we showed that when multiples of equations for two intersecting planes are added, the resulting plane will include the same intersection line as the original two planes. Depending upon the value of the multiplier, the resulting plane can be oriented in any way around the line of intersection. If a multiplier is chosen so that a variable is eliminated, then the resulting plane will be parallel to that variable's axis. For instance, if the variable z is eliminated, then the resulting plane will be parallel to the z-axis. This is exactly what happens during a pivot operation, except that one of the original planes is replaced by the resulting plane. So let's reduce a matrix to reduced row echelon form using Gauss-Jordan elimination and follow how the planes change their orientation with each row operation. We will start with a system of three linear equations and three variables, represented as an augmented matrix. Since this matrix represents a linear system in three variables, each matrix row corresponds to a plane in three-dimensional space. We will start by changing the first row's leading entry to a 1, using a scale operation to multiply row 1 by 1/4. Since a scale operation does not affect a matrix row's graph, this operation has no effect on the planes. Next, we change the entry below the 1 to a 0. We do this by using a pivot operation to add -4 times row 1 to row 2. Since the pivot operation adds a multiple of row 1 to row 2, it changes row 2 and causes plane 2 to rotate around its line of intersection with plane 1. And since the x coefficient in row 2 has changed to 0, plane 2 has become parallel to the x-axis. -4 times row 1 to row 2. Since the pivot operation adds a multiple of row 1 to row 2, it changes row 2 and causes plane 2 to rotate around its line of intersection with plane 1. And since the x-coefficient in row 2 has changed to 0, plane 2 has become parallel to the x-axis. Continuing to work. Continuing to work from the top down, we change the bottom entry in column 1 to 0, using another pivot operation to add -4 times row 1 to row 3. Since this pivot operation added a multiple of row 1 to row 3, this change to row 3 causes plane 3 to rotate around its line of intersection with plane 1. And since the x-coefficient in row 3 has changed to 0, plane 3 has become parallel to the x-axis. Now we move to the second column, changing the second row's leading entry to a 1, using a scale operation to multiply row 2 by 1/16. Once again, a scale operation has no effect on the planes. The entry below that one is then zeroed, using another pivot operation, adding -9 times row 2 to row 3. Since this pivot operation added a multiple of row 2 to row 3, pivot operation is there's no effect by 1/16. Once again, a scale operation has no effect on using another pivot operation, adding -9 times row 2 to row 3. Since this pivot operation added a multiple of row 2 to row 3, The change to row 3 causes plane 3 to rotate around its line of intersection with plane 2. And since the y coefficient in row 3 has changed to 0, plane 3 has become parallel to the y-axis. Since plane 3 is now parallel to the y-axis as well as the x-axis, it is perpendicular to the z-axis and horizontal. And horizontal. Moving on to column 3, we then change the third row to a scale. It has no effect on the planes. Now we work from bottom to top, changing the entry above the 1 in column 3 to a 0, using another pivot operation to add 1/4 times row 3 to row 2. Since this pivot operation added a multiple of row 3 to row 2, the change to row 2 causes plane 2 to rotate around its line of intersection with plane 3. And since the z coefficient in row 2 has changed to 0, plane 2 has become parallel to the z-axis and is now vertical. Since plane 2 is now parallel to both the z and x axes, it is perpendicular to the y-axis. Moving up to the top entry in column 3, we zero that entry with another pivot operation, adding 1/4 times row 3 to row 1. To rotate around. Plane 1 has become parallel to the z-axis and is now vertical. To finish the row reduction process, we move to column 2 and zero the top entry using a pivot operation to add 1 times row 2 to row 1. Since this pivot operation added row 2 to row 1, plane 1 rotates around its line of intersection with plane 2. And since the y coefficient in row 1 has changed to 0, plane 1 has become parallel to the y-axis. And since plane 1 is now parallel to both the y and z axes, it is perpendicular to the x-axis. Since plane 1 is now perpendicular to the x-axis, plane 2 is perpendicular to the y-axis, and plane 3 is perpendicular to the z-axis, the equations for those planes allow us to directly read off the values for the variables x, y, and z. values for the variables x, y, and z. To reduce row echelon, many different ways that an augmented matrix can be reduced to reduced row echelon form using elementary row operations. Depending upon the particular sequence of row operations used, the intermediate orientations of the planes during the process can be different. However, once the system is in reduced row echelon form, the end result will always be the same. Regardless of the sequence of row operations used to get to reduced row echelon form, only the pivot operations change the orientations of the planes, each pivot operation causing a single plane to rotate around its line of intersection with the other plane used in that operation. If the system has a single unique solution, each plane will end up oriented perpendicular to one of the three axes, allowing the x, y, and z values of the solution to be read directly from the matrix. In the next lectures, we will see what it means for a system of linear equations to be dependent and what happens to dependent equations and planes during the process of Gauss-Jordan elimination.